Additive manufacture enables rapid construction of novel antenna designs in configurations not achievable by conventional machining for materials with enhanced strength and heat flux tolerance. I'm Andrew Saltzman from the Massachusetts Institute of Technology, and today I will be discussing our work on additive manufacturing applied to the construction of a lower hybrid RF launcher. 400 Celsius bakeouts in DIII-D anneal oxygen-free copper to 50 megapascals yield strength, below the required 200 megapascals to prevent launcher damage from disruption loads, while precluding copper-plated Inconel due to high-temperature diffusion. Additive manufacture from a high-strength copper alloy is used to address this design constraint. A novel high-field side launcher includes a traveling wave poloidal splitter and aperture impedance matching structure to reduce peak electric field below the multipactor breakdown limit. Elimination of standing waves reduces electric field by 20% compared to a standing wave power divider. Circulating power within a multijunction returns reflected power to the plasma. However, the resulting standing waves within the launcher increase the electric field, limiting power handling capability. A thin inductive impedance matching structure is integrated into each waveguide aperture to match waveguide impedance to plasma surface impedance, improving coupled power. By selecting an appropriate matching element height, the optimum coupling region, indicated by lowest electric field, shown and plotted in green, may be centered on the expected edge density, indicated by the blue horizontal line. In this manner, a launcher may be specifically matched to the edge conditions. The complexity of the matching structure and traveling wave divider is enabled by additive manufacturing techniques. While conventional machining of poloidal splitter and phase shifter frames from copper chromium zirconium alloy is possible, loss of strength would occur due to annealing at bakeout temperatures in DIII-D. During splitter assembly, electron beam or laser welding cover plates onto the splitter frame resulted in warping due to heat input and contraction at the weld joint. Additive manufacture eliminates internal machining and welding of cover plates. Complete parts, including diagnostic horns, waveguides, phase shifters, and poloidal splitters, are printed monolithically. Additive manufacturing with laser powder bed fusion is an enabling technology for complex launcher and waveguide structures. A powder is dispersed on the surface of a build plate with a coater blade. A cross-section of the part is consolidated by melting with a scanning laser under an inert argon atmosphere. The build plate retracts downward by the layer height and the process repeats. A build plate can be completed in 2 weeks at a cost of $10,000 to $20,000. Powder costs $300 per kilogram and is reusable. Current build volume is limited to 250 by 250 by 300 millimeters, as filling larger volumes with powder would be prohibitively expensive. Launchers are printed from GR-COP84 gas atomized powder. Originally developed for rocket engine combustion chambers, Glen Research Copper 84 maintains high strength at high temperatures and heat fluxes exceeding 100 megawatts per square meter. Niobium chromide precipitates form during the rapid cooling of gas atomized powder, increasing tensile strength. Additive manufactured GR-COP 84 achieves mechanical properties exceeding conventionally manufactured materials. Laser powder bed fusion reduces precipitate size compared to gas atomized powder. As 2/3 of the strength of GR-COP 84 comes from the precipitates by the Orwan mechanism, the greater number of small precipitates results in a material much stronger than can be achieved if the material was consolidated using hipping or extrusion from powder, where the initial precipitate size is maintained during the consolidation process. Heat treatment of additively manufactured GR-COP 84 controls precipitate size to select desired tensile properties. Heat treatment to 900 Celsius for 5 hours results in saturated coarsening of precipitates and a yield strength of 300 megapascals, exceeding the 200 megapascal yield strength required to withstand disruption loads. Additive manufacture of phase shifters eliminated internal machining of tapers and welding of cover plates. Phase shifters for 3 launchers are printed per build plate with dimensions within 10 to 40 microns of the specified value. Internal supports are required to prevent collapse of the ceiling into a horizontally printed waveguide. However, support removal requires physical access and produces a rough surface. Horizontally printed poloidal splitters are modified for compatibility with the additive manufacturing process by utilizing a pentagonal waveguide cross-section that supports the ceiling with 45-degree chamfers connecting to the sidewalls, thus eliminating the need for internal supports. A step discontinuity in waveguide cross-section occurs where the pentagonal cross-section of the poloidal splitter waveguide connects to the rectangular cross-section of the phase shifter. For a high aspect ratio waveguide, the impedance and mode structure of a pentagonal or hexagonal waveguide are almost identical to a rectangular waveguide with a reduction in broad wall height of equivalent area. Analytical formulas for impedance transform and reflection coefficients of a broad wall step discontinuity are nearly identical to finite element simulations of a pentagonal rectangular junction. Return loss below -37 dB is expected. Reduction in waveguide cross-section results in an increase in electric field, slightly reducing density limits of the launcher. Space constraints required additive manufacturing in segments. Laser welding must be used to assemble the launcher. 40 welds around waveguide perimeters and 5 septum welds are required to assemble each launcher module. Chemical mechanical polishing smooths inaccessible internal surfaces with a combination of chemical and mechanical action. A slurry of etching chemicals and abrasive beads are passed through the internal structure of the phase shifters and power splitters. The chemical etchant simultaneously etches and coats the copper surface with a chemical resist layer. The motion of the abrasive wears off the resist layer from the peaks, but not the valleys of the surface. Further etching of the peaks then occur. This process is continued until the surface is polished flat. An SEM micrograph of an as-printed surface with RMS roughness of 4.1 microns is shown on the top left. After CMP, the roughness is reduced to 0.4 microns as shown on the bottom left, resulting in low RF loss. Active brazes are utilized to join titanium, zirconium, molybdenum limiters to the plasma-facing surfaces of each launcher aperture. GRCOP84 has brazing characteristics similar to oxygen-free copper and copper chrome zirc. A TZM GRCOP TZM sandwich, shown on the left, is used to balance internal stresses. Limiters are then wire EDM cut from the plates and laser welded onto the poloidal splitters as shown on the bottom. Fixture plates provide stability and alignment of launcher components during welding while allowing beam access for perimeter welds. Laser welding assembly of the launcher starts from the apertures and moves towards the input waveguide. Unlike many copper alloys, GRCOP84 has excellent laser welding properties due to good coupling with both neodymium YAG and fiber lasers. Top and bottom full penetration weld beads are smooth with minimal spatter. Welds maintain 450 megapascals ultimate tensile strength. The first additive manufactured LHCD launcher was completed at MIT in October. Additive manufacturing enabled a novel RF design and resulted in improved mechanical properties, while surface roughness was addressed with chemical mechanical polishing. Future launchers may be printed as monolithic units, thereby eliminating welding. Thank you for your time. I will now address any questions you may have.